We shall next discuss normal forms. So, as mentioned before, the objective of discussing normal forms is the following. So, given a language like, say, a power n, b power n, c power n, or say a power n factorial, or things like ww, where w belongs to a comma b star, we wish to know whether a context free grammar exists for this, and if not, how do we show that there is no CFG for this? Can we come up with a tool like pumping lemma, using which can we show that there are languages which are not context free? So, to understand context free languages, and so that you can bring some insights, and with that we talk about properties about non-context free languages. So in an attempt to understand this, we need something called normal forms, and to talk about normal forms, we should also know how to simplify context free grammars, which is what we have discussed recently. How to simplify a given context free grammar. Given context free grammar may contain epsilon transitions which can be removed, and it may contain unit productions, it may contain symbols which are useless, and it may contain a string over terminals and non-terminals which may not be reachable from the start state. So such things can be removed. So having seen the first part, which is simplification of CFG, next we shall discuss normal forms. Under this banner, we will be discussing two things. One is Chomsky normal form, CNF. The next one is Griba normal form. So the GNF, the normal form ensures that the productions are written in some specific order, and with that one can observe some properties which will help us in understanding context free languages. Subsequently one can talk about non-context free languages. So let's look at CNF. So Chomsky normal form is defined as follows. You say, let G be a context free grammar. G is in CNF if every production in G is of two types. Either it is of this form, A implies BC, or A implies small a. So what is small a? A is a terminal, and A, B, C are non-terminals. Most importantly, it is defined for languages for which empty string is not part of this. Okay. So note, epsilon does not belong to L of G. Okay. So the grammar accepts non-empty strings, and for such a grammar one can represent, we say G is in CNF if every production is of this type. A implies BC, which means you have exactly two non-terminals on the right, or A implies small a, which is just a terminal. Either a non-terminal implies a terminal, or a non-terminal implies two non-terminals. That is all. Fine. And epsilon is not part of the language, so therefore we will not have a implies epsilon and all that. So given a CFG, some arbitrary context-free grammar, we first apply our simplification algorithm. We simplify CFG, meaning remove epsilon productions, remove unit productions, remove useless symbols, and subsequently we go for converting our simplified CFG into a Chomsky normal form. Let's take an example and see how things work as far as this procedure is concerned. Consider this grammar. S implies small a and S implies AS and A implies small a. Now if you look at this, each production is respecting CNF condition. S implies a terminal or exactly two non-terminals, therefore this is in CNF. And for example, given a CFG, we wish to know whether an example like this is in CNF or not. First, one has to apply the simplification procedure. But if you apply simplification procedure, you will get this itself, because there are no epsilon and there are no unit productions and there are no useless symbols. And then we check whether is this respecting CNF properties. Answer is yes. Therefore, this grammar is in CNF. Let's look at this. S implies ASA and A implies epsilon. S implies A implies this, or A implies B implies epsilon. Okay, and let's look at S implies AB. Let's assume that this is our CFG. So the first step is to simplify. So as part of simplification, we need to remove epsilon transitions. Now S implies, if you apply this, you get ASA, or you apply epsilon for this, we get SA. You apply epsilon for this, we get AS. You apply epsilon for both, then we get S implies S. And then we get to see that S implies AB. So you get A, or you get B, or you get epsilon. Okay? Because both can be epsilon, which is why we have written this. Now, S implies small a and A implies this, or when you apply epsilon, you get this. Similarly, A implies BB or B. That's all. And you can remove this now and this, and everything else is taken care of. Fine. Now the next step is to remove unit productions. So when we remove unit productions, we get to see S implies A is allowed, SA is allowed, AS is allowed, and S implies S is a unit production, and S implies A is a unit production, S imply B is a unit production. So S implies SS, you simply write this. S implies A and A implies this. So therefore we get this or this, and we get BB this, and S implies B and B implies no productions. So which means S implies A, S implies B, S implies S. All that can be removed. So apart from this, we have S implies A, anyway it is already written, and A implies AA, or this, A implies BB, or this. Remember, this is also giving us this, but we know if we want to check whether it is in Chomsky normal form or not, Chomsky normal form exists when the language is not containing empty string. Otherwise, we don't write Chomsky normal form. Okay. But when you simplify this, we see that S implies epsilon. So therefore, we simplify and stop our procedure. We do not further simplify the grammar and look for CNF. Okay. So let's continue this. So from this, when you remove unit productions, you see that S implies S, and S implies A, S implies B, and S implies A you can remove by including this. That's all done. But S implies B, B implies this, no production, so that can be removed. Fine, and this is all we have. Now, are there any useless symbols productions? Now, from this you can reach ASA and SAAS. Now, look at this. This says S implies BB, and this also says A implies BB, but we do not have any productions with non-terminal being capital B. So which means S implies BB is a useless production, and this is also a useless production. So on further simplification, what we get is the following. S implies ASA or SA or AS followed by epsilon, or S implies AA small a or B. S implies A is already covered, and A implies AA or this, A implies B. So when you move from this to this, we have removed this as well as this, because starting from S, when we reach BB, we cannot generate any meaningful string because there are no further productions with this. Okay, now we stop here and we cannot do any further conversion because the language itself contains epsilon. Okay, so for this, no CNF exists. So we simplify and stop our procedure. Consider this grammar. S implies ASA, S implies BSB, S implies A or B. So now we see that S implies A or S implies B. This is in CNF, but these two are not. Most importantly, for this grammar, the simplified grammar is also this. There are no epsilon transitions and there are no unit productions and all symbols are reachable. So now when we try converting this into CNF, we get S implies A, S implies B, and for this, what we do is we say S implies A1 followed by A2. We say A1 implies small a and A2 implies SA. Okay. Now, this is in CNF because it says two non-terminals are allowed. This is in CNF. This is not in CNF. So what we will do is, this will be rewritten as A2 implies yes A3 and A3 implies small a. On the similar line, this one we say S implies B1, B2, B2 implies yes B3, B3 implies small b. So which means the resultant CNF is the following. S implies A1, A2, A1 implies A, A2 implies yes A3 and A3 implies small a. Fine. Also, S implies B1, B2, B2 implies yes B3, B3 implies B. In addition to that, these two, S implies A and S implies B. Now we see that for each one, we find exactly two non-terminals or one terminal. Two non-terminals, one terminal. So since each production is respecting the CNF property, it is clearly in CNF. Most importantly, this grammar G prime, the language accepted by G prime is same as language accepted by G. Okay, so while doing this simplification, we ensured that the equivalence is maintained, meaning the strings that are generated by this and strings that are generated by this, they are one and the same, or in particular the language accepted by this and this are one and the same. So now for an arbitrary grammar like this, first we go for a simplification. On the simplified grammar, apply a trick like this so that you get to see a grammar, and a grammar which is equivalent to this respecting CNF property. So when you find something like a non-terminal followed by a terminal, replace this by another non-terminal. So which means while trying to construct CNF, we introduce non-terminals. So for this, if you look at n consisting of S, A1, A2, B1, B2, A3, B3, and terminals, they remain the same, and start symbol is again S, and there will be a change only in the set of non-terminals. Fine. One can take a sample string and derive using CNF and see how the underlying parse tree looks like. Does the parse tree, does it have any unique structure which will help us in analyzing context-free languages and followed by non-context-free languages? Basically, the insights we get out of this, will it help us in analyzing non-context free languages? All that we shall explore.